Hello everyone. In this video, we are going to solve the AXI4-Lite homework problem from the previous lesson. The goal is to design an AXI4-Lite random access memory slave in Verilog. To do that, we will combine AXI4-Lite write commands and AXI4-Lite read commands into one complete IP block. After the code is explained, we will also show the Vivado and Vitis setup used to test the RAM with the MicroBlaze processor. This lesson ties the previous two lessons together. In the write command lesson, we designed a custom IP block that accepts AXI4-Lite write commands from the processor. In the read command lesson, we designed a custom IP block that accepts AXI4-Lite read commands from the processor. In this video, we combine both ideas into one complete AXI4-Lite slave that supports both reads and writes. Before watching this video, I recommend watching the previous videos and I recommend attempting the homework problem yourself first. The previous lessons explain how AXI4-Lite write commands work, how AXI4-Lite read commands work, and how to set up the Vivado and Vitis project. If you understand the solution to the homework problem, then you understand everything needed to make a custom Verilog module communicate with a processor using AXI4-Lite. Alright, let's get started. This was the homework problem from the previous lesson. The goal was to design a RAM with 8 locations that the processor can write to and read from using AXI4-Lite. Before building the RAM slave, we will briefly review the AXI-Lite write process and AXI4-Lite read process. So this is the summary of the AXI4-Lite write command. When the processor executes a write command, the Verilog module uses the pink signals as inputs and the green signals as outputs. The rules below summarize the entire write process. For the full explanation, watch the previous lesson on AXI4-Lite write commands. So this is the summary of the AXI4-Lite read command. Again, the pink signals are what the slave uses as inputs, and the green signals are what the slave uses as outputs. For the full explanation, watch the previous lesson on AXI4-Lite read commands. Before looking at the code, it's important to understand the solution strategy. The RAM slave is created by combining the two IP blocks from the previous lessons. The write logic from the start pulse IP and the read logic from the ROM IP can both be reused. Together, these two pieces can be used to create the complete AXI4-Lite RAM slave. Alright, so this is the Verilog code for the AXI4-Lite RAM slave. On lines 1 to 32, we declare the module and the ports. The ports for the write bus are declared and the ports for the read bus are declared. On lines 50 to 59, we declare the 8-location RAM, declare 2 integers used by the loops, and initialize every RAM location to 0. On lines 65 to 76, we define the 5 states and registers used by the write logic. On lines 78 to 188, we implement the AXI4-Lite write logic. This block is almost the same as the write logic from the start pulse IP, but the main difference is on lines 157 to 166. Instead of generating a start pulse, as was done in the previous lesson, these lines now use the saved write address to select a RAM location and write the saved data into it. Each RAM location stores 32 bits, which means each location contains 4 bytes. During a write command, the slave uses both the write data and the strobe signal to implement the full AXI4-Lite write behavior. The strobe tells the slave which bytes should actually be overridden. For example, if the strobe is 0001, then only the first bytes, bits 7 through 0, get updated. The loop on lines 158 to 162 automates this strobed-based byte masking behavior. For normal 32-bit AXI writes, you could ignore the strobe and overwrite all 32 bits directly, but this version shows the more complete behavior. On lines 194 to 202, we define the 4 states and registers used by the read logic. The remaining lines implement the AXI4-Lite read logic. This is the same read logic used in the ROM IP from the previous lesson. The only difference is that the memory being selected is now RAM instead of ROM. Now that the source file for the RAM IP is finished, store it in a known directory. This is where I am storing mine. After that, open Vivado and package the Verilog file as a reusable IP block. To package the IP, click Tools, Create and Package New IP, then select the source file from the directory where you saved it. Then, when the pop-up window comes, click the button to package the IP. After packaging the IP, you can assemble the block design yourself. This is the block design you will make. It is the same design from the last video, but with the RAM IP replacing the ROM IP. After the block design is complete, generate the HDL wrapper, generate the bitstream, export the hardware, program the device, and open the project in Vitis. After Vitis has launched, create a new application project. Then select the file that you exported. This will be an XSA file type. Give your project a name, then create an empty C application. Once the project is opened, create a file to run your main program in. Then paste in the demo code that we will use to prove that our design is working. Then click the hammer to build it. This code writes values into all 8 RAM locations, reads those locations back, and prints the results to the serial terminal. It does this repeatedly by writing 0 to 7 into the 8 RAM locations, then 100 to 107, then 200 to 207, and so on. Then add in the Vitis serial terminal. After adding in the Vitis serial terminal, click the green plus sign and connect it to the board. Make sure the settings you choose are the same ones that your UART block used in the block diagram. Then to run the code, click on Run Configurations, then System Project Debug, click Target Setup, then uncheck Program FPGA, then Apply and Run. An error happened because the FPGA was not programmed yet. To fix it, program the device in Vivado, then run the Vitis code again. In the serial terminal, we can now see the program running in real time. The terminal is printing the correct values, which means that the custom RAM IP is working. We know it is working because the Vitis code as written cannot print the correct values unless the processor is successfully writing data into the RAM IP and reading that same data back out. So there you have it. You now have seen how to design an AXI4-Lite slave that supports both reads and writes. Using this knowledge, you should be able to connect any Verilog module to a processor by making it properly handle AXI4-Lite read and write commands. Alright, that's all for this video. Looking forward to seeing you next time.